Good evening, everyone. Welcome to the week 3 TA Office Hour for Business Analytics. How has everyone been doing in the past week?
Fabulous, thank you.
Oh, glad to hear that, Donald.
Hanging in there.
All right, Christina.
It's been rough.
Did you say it's been less? That means it sounds easier this week?
No, it's been rough.
All right, Michelle. Any suggestions or questions regarding how I can make the process easier for all of you?
Hey, Jerry, I had a question on the homework that's due tonight.
All right.
Okay,
so let's go straight forward to our homework questions.
Yeah, so in problem number 1, so I understand how to create the scatter chart and whatnot, but I guess my only question I think I had was I think I have two. When it asked for a regression equation, so when I did it on Excel, it spit out the Y equation, but is that not the regression equation? Is it something different? I guess I thought that was the regression equation.
Okay. I'm not sure whether I actually caught the center of the question. You said you run a regression, but you're not sure how to report the regression equation.
Right?
Correct?
Right.
So what do you have now? And what did you put there as a
the equation
candidate
that I have?
Yes.
Yeah. So the question was, develop a simple linear regression model with price as a dependent variable. What is the regression equation? So I had Y equals minus 1528.6x plus 30287. So, but there was some discussion earlier between us that in class, he had like the epsilon sign at the end. And so is that necessary for us to put as part of our equation?
Yes, correct. The epsilon symbol represents the error term, which suggests that this is a not perfect prediction, but a regression model.
Okay. How do you make the epsilon sign?
Well, yeah, good question. So you could find if you want, you could search on Google saying epsilon sign, then you could copy and paste that symbol as a character. However, you can simply just type error term. So let me show you because the other class also had a similar question. So what Arena was wondering for other students, and just so you know, was question problem 1 in homework 3, part C. So we are here to find a good way to report the regression equation. And let me share my screen. All right, here we go. So in the past week, we have learned a simple regression, linear regression model using one variable to predict another. So in problem 1, we are predicting the price of a bike using its weight. And if you did the homework, then you know that this is the summary output of a linear regression model. And we have regression statistics, ANOVA, and some coefficients. So here, for part C in problem 1, how to report a linear regression equation. A temporary solution is like this. What Irene reported was, instead of price, she used Y, and instead of weight, she used X, which is fine, but we could be more explicit here to say that we are predicting price using weight. And she was particularly concerned about this error term. So as I wrote here, you could simply write error here.
Oh, we actually write out the word error. I see.
Yeah, you could do that.
Got it. Okay.
Yeah, if you prefer a symbol, you could find this character on Google.
Got it. Okay. Thank you. Oh, sorry, Jerry, can you just explain? Because I know you said that if we were to do the y equals, negative 1528.6x, that would be okay. It's not quite wrong, but it would be better to do it in this. Can you explain why this would be better?
Yes, sure. Because usually when you report an equation, it's potentially in the appendix of any data analysis report. Usually you don't put it in the text. And here you want to be very clear about what, if you used any symbols like X and Y, what they represent. Here we don't have to go through that extra procedure. So we are very clear saying that the dependent variable is price and the independent variable is weight if we formulate in this way. Otherwise, if we used y equals an intercept plus coefficient times the independent variable, if we used x, then for readers, in the beginning, they won't be sure what X and Y represents until you tell them.
I see.
So you need another, you would need another sentence saying that where X represents weight and Y represents price. So we simply saved that extra effort.
I see. Okay, it's just making it clearer for the reader. Got it. Okay.
Yeah. Excellent. So it seems you have been doing pretty well in terms of many homework questions. Any more homework questions? Or any general questions?
Jerry, do you mind reviewing how you got the predicted price? Because I was just kind of just inserting my weight into the equation, but is there another way we should be looking at this through Excel, like looking at what was the data that was given to us, and then from there making a predicted value, or looking at the regression equation in a different way? Because I was just kind of plugging in X and then getting Y. Okay.
So it sounds like you were wondering about part F for problem 1. Is it correct? How to make
the
a
predicted
prediction
value. Yeah.
So could you elaborate how you tried to do it?
So I just simply took the weight that that we were trying to make a prediction for, and that was my X, and then I solved for Y. So, but I'm thinking or wondering there's more to it, or that we were supposed to do something on Excel with the data that was provided to us.
Oh, okay. Could you actually show us how you did it? You could describe how you did it, or maybe share your screen with us. So I'm not sure what you actually meant by plugging in the values instead.
Oh, I just literally like, I don't know if you could see.
Yeah,
what you could
I'm
see.
seeing your screen you shared.
Okay, so I mean, I just said when X equals 15.5, my Y equals, and then I got this number. So that's what I'm saying. I just.
How did you get the number though?
I put it into the regression equation.
Oh,
I
and
put it into
did you
this.
calculate it manually?
Yes, yes.
Oh, okay. Yeah, it's actually quite fine. You're doing it in the correct way. It's actually what the regression equation is for. It helps us to make predictions.
Right.
Yeah, so you're doing it in a correct way. Although some other students could have done it by manipulating the Excel cells and values to calculate that number for you instead of calculating it manually.
Can you show us? Can you show us that way?
Yeah,
so that I understand better.
So, oh, there are some questions in the chat. I'll come back to the chat area later. Let's check. Was it Karen earlier? first question. Let's go to another screen share. Okay. So I'm pretty confident that all of you have went through this linear regression estimation process that where Excel generates a summary output, right? And
Yes.
to make predictions, like a question in part F, we would mostly use coefficients. These coefficients can also be known as slope or beta in some other parts of the homework. They are in some other statistical programs. This column or coefficients can be also called estimates. Just so you know, you don't have to be afraid or panic when seeing the same content or statistics referred to by different terms. With these coefficients, how can we make predictions? Let's make an example. Since we already get the linear regression equation, like what we just practiced for part C, I believe, we use the same form to do so. So for example, what was it Michelle's question for part F? Yeah. When we make a prediction, for example, if we want to predict the price, when weight equals 16.5 pounds, or maybe kilograms, I don't really know the unit. However, we put the prediction as this: the true value of a bike equals with a weight of 16.5 would be like this. We plug in 16.5 in the regression equation. However, what do we need to do with the error term? So remember that when we studied the linear regression models, we had quite a few assumptions. One of them being that the expected value or the mean value of the error term equals 0. So that's where it plays a role here. Because the expected value of error is 0, so for an expected value of price for a bike with weight of this much, then we simply have 0 as the expected value of error. And as you can see, the error term would be going away. So this would be the expected value of a price for a bike with weight equals 16.5. So how do we calculate it? Actually, we could actually use the coefficients we already have. So this is the result, which I calculated using this function. As you can see, it refers to both of the coefficients. Simply, I used E40, that's the intercept, plus, remember, we have to do plus, although the coefficient has a negative estimate. E41, which is the coefficient for weight, times the weight that we want to predict for the price. So when we plug it in, it simply represents the regression equation as I showed here. So that's the value we calculated based on the regression equation I showed in this cell in column F. I hope it addressed your question pretty well.
Yes, thank you.
All right, Karen. Any more questions?
Jerry, can I ask a question about problem number 1?
Yeah, sure.
So When I just looked at the scatter, and I was looking back at Thomas's videos, when you break up the quadrants, it looks like the scatters the data points are in quadrant 2 and 4. So in a positive quadrant and a negative quadrant.
Mhm.
So I was just assuming that it would not be a strong relationship because they would cancel each other out. But then when you actually run the regression model, it's very strong.
Mhm.
0.95. Am I like thinking about that the right way?
Oh, okay. Unfortunately not. I think you had
Shocker.
a misunderstanding of
Okay.
um, uh, correlation or linear relationship.
Okay.
So I'm assuming you saw this, you did the scatter plot with the origin where the x and y axes intersect at a different point other than 0, 0. So that's why you probably have seen it in different quadrants, but points being in different quadrants of a coordinate does not suggest that they have strong or weak relationship. So how about you share your how about if you share your scatter plot you made with us so I can point out.
Sure. Let me grab that.
Well, sharing screen from your phone. I haven't done that myself. Excellent. So it doesn't seem you have different quadrants to worry about. Maybe you made a different plot earlier.
Sorry, let me unmute myself. I couldn't, yeah, I'm on my phone. Let me show you unmuted. Sorry, now it's not working.
Oh, okay, no problem. I already saw the screen you shared with us.
Okay, thank you.
Was it a plot you made that where you had questions?
No, it just, the first question was just asking like, what do you make of this?
Mhm.
Just of the scatter. And I think you're right. What I didn't, the quadrants just ended up on the wrong, the plots ended up on the wrong quadrants, and I had a misunderstanding or misinterpretation of that. But then when I actually ran the
Okay.
regression and put in the trend line, it was quite strong.
Yeah. So let's see how I can help you illustrate this part. I saw a quite useful web or ebook where they showed examples of correlation coefficient and the actual relationship. Let me find it. Okay, yeah, here we go. Let me share my screen of an online ebook I used to do time series analysis, which is somewhat similar to previous examples we worked on for stock price relationship. So this ebook is called Forecasting Principles and Practice. It uses R, another statistical package, just like Excel, to do data analysis. And in a section, it shows us some examples of correlation. So these are scatter plots and with the independent variable on the horizontal axis and the dependent variable on the vertical axis. And as you can see, if we have strong relationship, either it could be strong negative relationship when X increases, Y decreases, or strong positive relationship where Y increases with X. Yeah, so both ways would mean strong relationship. So don't get confused between the direction and the strength of the relationship. These are two different things. Yeah, so
that makes sense. Perfect.
And as you can see what it means by negative and positive relationship. On the first row, let me enlarge my screen. On the first row, all four plots suggest a negative relationship. Basically, it has a downward trend, as you can see. And on the second row, all these four plots have suggest positive linear relationship. As you can see, it has an upward trend. And you can also tell out of the scatter plot how strong the relationship is. This strength can be revealed by how close the dots are centered around a trend line. As you can see, if it's almost a perfect linear relationship where the correlation coefficient equals either positive here or negative on the upper plot, 0.99, then all the points are centered almost along the trend line. However, if their linear relationship is not as strong, meaning that the points are more scattered away from the trend lines, then we could find that the correlation coefficient would be lower. Either it could be negative or positive, but it'll be closer to 0. So these are the different examples of strength and directions of linear relationship. However, the reason why we have practiced a few times of doing plots instead of reporting simply statistics is very important, because the plots actually tells us more information sometimes or almost always than a simple linear regression coefficient. So what extra information can we detect from the plot instead of using a coefficient alone like this 0.99? Is that there are other cases where we find that this plots with the same correlation coefficient can actually have very different shape. So let's take another look. In these four plots, as you can see, each of these plots has a correlation coefficient of 0.82. So if you simply report a correlation coefficient, any of these plots will give you 0.82. But do they actually reveal the same relationship between the X and Y? As you can see, no. From the upper left plot, we can see that they're somewhat along, they should have a linear relationship, right? But on the upper right plot, we find that this is actually a quadratic regression where we find a quadratic curve. And on the third one, bottom left, we find the relationship is actually mostly driven by an outlier. All other points are centered perfectly on the trend line except for one point. And the lower bottom, although it shares exactly the same correlation coefficient with all the other three plots, it reveals almost maybe no relationship between X and Y, because when X is fixed, Y changes from 5 to 9, right? Except for one point, it might be an outlier. We need to check it later. So when we find either a perfect vertical line or perfect horizontal line, we would say that X and Y do not have strong or even any relationship, because knowing one of the value does not help us to predict another. For example, here in this plot, the reason why I quoted that relationship between X and Y is almost does not exist, and because X is mostly fixed at one value, while Y changes between a range. So knowing Y does not help us predict X, and knowing X does not help us predict Y. So that's why. All right, so great. Thank you.
Thank you so
Michelle,
much. That was very helpful.
to point us for a review of correlation and linear relationship based on scatter plots. So yeah, a tip, always very good to plot the data first before running into analysis. All right, let me go to the comment area. I noticed that a few students have raised questions. Oh, I see. So after Karen, a student said about Y hat. So maybe some of you have heard of this term in other reference books about Y hat or some other symbol with hat. The hat is a typical way to symbolize a predicted value.
Hello?
Hi, is that Karen?
Yes. I'm sorry. Can you hear me?
Yes, I can.
Okay. I know you're moving on to the questions, but what you just showed earlier with the different scatter plots.
Yeah.
I don't really understand what you were saying, other than that all those plots have the same correlation coefficient, but they all look different. And that's because they have a different regression, or I guess I didn't understand what those plots meant, other than that they all have the same correlation coefficient.
Were you not sure about the first or the second set of plots I showed?
Second, I think it was.
Let me go back to the web page. So were you curious about this part or this part? Hello, Karen.
The second one, sorry.
All right. So let's simply read the figure title again. Each of these plots has a correlation coefficient of 0.82. However, when we look at those plots, they actually reveal very different relationships. So that's why it's important to check, to plot data in addition to using statistics like correlation coefficients.
Because even though they have the same correlation coefficient, their regression model might be different.
One of the reasons, yes. If you run regression models of them, of course, they will be different. you will have different intercept and coefficients reported in the regression. However, the plot mostly would tell you what type of regression would be most appropriate. For example, based on the top left plot, I would think using a linear regression model, like a simple linear regression model, like what we did for the bicycle price and weight example would be appropriate. However, if we move to the second or the upper right plot, I would say that using also a linear regression, but with quadratic terms would be most appropriate. You will learn about adding a quadratic term next week, I believe, if not the week after the next. So in this plot, we would only need one predictor as x. In this plot, we would need two predictors, x and the square of x.
Okay, I see.
Yeah, if we compare plot 1 and 3, the upper and the bottom of left, then we will find that if we run a regression model, they would give us different coefficients of the regression model. But they also tells us that the linear relationship, the strength of the linear relationship is somewhat different. As I said in in the bottom left plot, we will probably find that the second last point might be an outlier. We need to be more careful about whether to include it or not in our model. Yeah, and in the last plot, as I said, it reveals basically no relationship between x and y. So we don't have to run a model. It won't be very useful to use a model to describe the relationship.
So how are they all the same correlation coefficient?
Yeah, that's because the correlation coefficient is defined as this. It only tells us the strength of a linear regression, how much of the variation in one variable is can be explained by another. And the correlation coefficient only reveals linear regression, linear relationship. That's why if we have quadratic relationship, it poorly describes the data. So it won't be really appropriate to report correlation coefficient if we have nonlinear relationship.
So is there another name for correlation coefficient for nonlinear relationship?
No, no. But there are other versions of correlation coefficients that could be more appropriate for data that's based on ranks of the value instead of the original value. But these would be somewhat more advanced correlation coefficients, and they won't be most widely used version. When we refer to correlation coefficient, we usually refer to the basic version. It's also known as the Pearson correlation coefficient. It only reveals the linear relationship strength.
Okay, thank you.
Yeah, if you're interested in exploring why they could possibly have, and if they actually have the same correlation coefficient, although the plots give us suggest very different shapes of the trend curve, then you could go to their paper and find the original data and practice for yourself.
Thank you. I don't think my math will understand that.
Yeah, well, I'm just here to remind everyone that a correlation coefficient doesn't tell us everything. It's quite important to plot the data.
I have a question.
Hi, could you help me read your name?
Yuichi.
Yuichi. Okay,
Yes.
excellent.
Okay, so I understand that you had the correlation coefficient, which is the relationship between two variables, x and y, in a linear regression. So that part I understand, but when it asks for the coefficient of determination, can you go over that? And if you have any visuals, just like the correlation coefficient, that would really help out.
Okay, yeah. So Yuichi brought up a very important question, the distinction between correlation coefficient and coefficient of determination, also known as R square. Some other students also had a similar question in the other class. So let me illustrate it with our problem 1. I'm sharing my screen again, where you will find the original data of problem 1 for bicycles. We had the models and weight as independent variable, price as dependent variable. So after running the linear regression, we know that there's a R square reported, and which Yuichi referred to as the coefficient of determination. And we also have a correlation, which is part of the question in part B. So what, why are these two statistics different, and are there any relationship? Let's review. Let's review their relationship by first understanding the correlation coefficient. We built between weight and price are done this way. We run Excel function correlation between this array and the array of weight and the array of price. That's how we got the correlation coefficient between weight and price. And because in the first part of the problem, we already know that it showed us a downward trend. So we know that they have a negative linear relationship. That's why this correlation coefficient is a negative estimate. However, we also have an R square, which is this figure, right? And how could we get this? First, note that we also had a multiple R here, which you can find is exactly the same magnitude with the correlation coefficient, except that it has a positive sign, not a negative sign. So how come that we had this?
Wait, Jerry,
So-
that's a coefficient determination, right? Not the correlation coefficient. I thought the correlation coefficient is R squared.
No, correlation
No.
coefficient is this one. The determination, the
It's R
coefficient
squared.
of the determination is R square is this one.
Oh, I haven't. That's
So
okay.
I was trying to show among us what's the relationship between these two. But in addition, I also want to point out there's an multiple R reported as part of the summary output. And I show that this multiple R has the same magnitude with the correlation coefficient between X and Y if we have only one predictor in a model, except that this multiple R is positive, but the correlation coefficient is negative, but they have the same magnitude. The reason is that can be seen this way. So first, we make expected or predict values of price using the model that we already estimated. For example, for the first item, Faro 7B, we predict the price based on the weight using the same way we did for part F. We basically add intercept and coefficient times the weight that we want to predict from. So we do this for every part, every item or observations. As you know, each observation is simply a row of the data. Then if we run a correlation coefficient between the original price and the predicted price, we find that this correlation coefficient has the same magnitude as the correlation coefficient between X and Y, weight and price, but except that it's positive. And this correlation coefficient between price and expected value of price is exactly what multiple R is. When you compare, these are the same statistic. It shares the same magnitude and sign. Are you all following me? So that's how we get multiple R. The R square is simply the square of this multiple R, as I calculated here. If we square the multiple R, that's exactly what we got in R square. So that tells us the relationship between correlation coefficient between X and Y and the R square. Because R square is squared statistic, it's always positive. So we know that if we square correlation coefficient, we get also exactly R square. That's what's calculated here. If we square the correlation coefficient, we get the R squared statistic.
Just a note, Jerry. So we know that the coefficient of determination will always be a smaller value when we take the absolute of the correlation coefficient. That's a correct statement, right?
No. What do you mean by absolute?
So the magnitude here is 0.9514. So if we square that, it's always going to be less than 0.9514.
Yes, numerically, yes, but it does not make sense to compare these two magnitudes.
Well, no, because one of the things is asking, like, what do we expect the value of the coefficient of determination to be? And that's always going to be a lower value than your correlation coefficient.
Yeah, that'd be true. But we can simply calculate it by squaring it. But as I said, it does not make much sense to compare these two statistics, saying that the R square is smaller than multiple R. It does not reveal any information. But what you said is true.
Okay. So then, do you have any visuals on explaining what the R squared is?
Visual. No, but I can explain. So we know that the R square is simply the percentage of variation in Y that can be explained by X. That's what R square means. But for visual, it's easier to see plots for correlation coefficients.
I see. So the R squared is basically the percentage of the total variation in your dependent variable, right?
part of it is right. You must add another term saying that that can be which can be explained by x,
Okay.
because the r square cannot, excuse me, cannot be calculated solely on one series of data. It must be based on at least two series of data. For example, in this problem 1, we have 2 series of data, weight and price. It does not it won't be possible to calculate in R square if we only know price. We must also have some other variables to predict price.
I see. Okay, I'm just trying to understand, like, because in the homework, it's asking us, like, what do you expect the coefficient of determination to be? I mean, other than saying the coefficient of determination R squared is this value, what else are they looking for here? And that's why I asked the question is, we expect it to be a smaller value of the correlation coefficient.
Oh, I see.
Right.
Well, you don't have to say smaller or larger. You can simply quote the results you got.
Okay.
The reason for, I mean, the logic behind this question is simply for students to understand that the relationship between correlation and R squared. If we square the correlation, then we get R squared.
Okay.
Oh, wonderful.
Jerry.
Hi.
Hi, it's Karen again.
Hi, Karen. How are you doing?
Can I ask you about problem 2B?
Yep.
Where it asks, what is the R squared of your regression model? What does it mean? This is the one talking about the stocks, Microsoft stocks and the S&P 500.
Yeah. All right.
So, okay, so for this one, my R squared is 0.36, but can I just tell you what I wrote and see if it actually makes sense? Because
yeah, sure.
It's kind of
Please,
confusing.
Yeah, please elaborate your
Okay,
candidate answer.
Okay, I said that it means there's not a good correlation because only 36% of the variation can be explained, and there's a high degree of variation between these data sets, and we wouldn't want to use this model.
All right. So this is all the explanation you had for R squared in part B.
Yeah.
Oh, okay. It's an okay answer, but first it missed some important interpretation, and second, it's not very correct in terms of the statement. So let's check both parts.
Okay.
By the first part that where I said that some important interpretation is missing, is because we first need to explain what an R square refers to. As I discussed with Yuqing, an R square is the percentage of variation in a Y or dependent variable that can be explained by X or independent variable. So in our case, we should first state that based on the R square, we find that 36% of the variation in Y, which is monthly changes in Microsoft adjusted stock price, that can be explained by S&P 500 stock price change.
Okay.
So first we interpreted this R square. And the second, to make some judgment about whether you're satisfied with the R squared or not. For this, I would say that be more conservative, not to expect a very high R squared. It rarely happens. So if we see that, for example, here, only 36% of our variation in Y can be explained by X, we won't say that directly S&P 500 is not a good predictor. The strength of the relationship, you can say it's moderate. It's not very strong, it's okay. But in terms of whether this model is good or not, should not be solely judged by this magnitude of R squared.
So the other factors that would affect it is like the slope.
Yes, you're right. However, in this example, we won't know what the other factors are.
Well, we know the beta.
Oh, sorry. What did you mean? Maybe I didn't catch your question.
Oh,
correctly.
this, I was saying there's other things in this model that
Oh, right.
could explain the relationship, but we know the beta. Does that affect how strong of a model it is?
No. So these are quite different things. So let's discuss one by one. So Karen here had a question regarding the meaning of or the distinction between a coefficient and R squared. Sometimes students will get confused between these two. Let me explain using the example. Okay. Oh, right. I'm still sharing the screen. All right. Then let's go to this example directly. In the stock price example, we estimated the coefficient of linear regression is about 0.9. Whereas the R squared is about 0.36. So these two statistics, estimated coefficient and R squared, reveal very different information to us. And they are not really comparable. So if we have a very high value in coefficient, it does not mean the R squared would be high or lower or low. So don't get confused between these two. So for example, if we got this R squared to be very small, for example, 1%, but we still get a coefficient that's, for example, 1, it does not reveal a strong linear relationship per se, because the coefficient reveals as the marginal effect. How much does Y increase when we increase X by 1 unit? But this R squared tells us the percentage of variation that can be explained. So the information between these two are not interchangeable. So don't get confused.
Okay, thank you.
Yeah, adding to that, you can find other situations where you estimate a model where you find this R squared to be very high, but the coefficient can be very small. It's also quite possible to happen.
So just to summarize, so basically the coefficient, which is the slope, it can be small, like a small change in x can determine small change in y, but the r squared, which is the correlation, could be big, like it doesn't correlate well, or it could be small where it correlates well. Is what you're saying?
Oh,
No.
no, and you also mistook quite a few concepts already. First, you misinterpreted the, there was some misunderstanding about what R square represents and what the value states about it. A higher R square reveals that a larger percentage of the variation in Y can be explained by X. So it reveals a stronger linear relationship. And what you said was the opposite. So don't get confused in this area. All right, any more questions about homework 3? All right, then let's make a very tiny practice to interpret the summary table, summary output of linear regression, just to make sure you understood each part of the statistics well enough. So first, let me share my screen, from which let's explain or interpret each of the statistics together. So in a summary output of the linear regression, first we see multiple R. We already practiced that because someone volunteered to tell us what the multiple R reveals, what the statistic mean here, what does 0.95 represent. And one of you unmute yourself and announce the answer.
You had mentioned that it's when you take the correlation of the predicted value and the actual data point, you'll get that same magnitude.
Excellent. Thank you, Nisha. All right, let's jump to this. What does 10 represent here? Can one of you tell us what 10?
I mean, it's your number of observations, right? So the number of inputs you're putting in your model.
Okay, yeah, excellent. So it's important to sometimes take a look at this because you want to make sure you selected the correct arrays of data in a model. I noticed that in previous classes, in previous quarters, some students select the data input for regression only on the numeric values, but they also select that this area or arrays of data include labels. So the Excel automatically treats the first row, that's the first observation, as the title or the name of the variable. So suddenly they lose one of these observations. So make sure that the model you had for Excel actually run on the desired number of observations. All right. Excellent. Thank you, John. Can someone tell us what the standard error refers to? It's 814.99, almost 815. Any guess?
At the variation between each of the observations.
A
Versus
good
the
try.
versus the
However,
line.
sorry, no, what did you say?
Is that
Never?
against the linear relationship?
It's related to that.
Is it your epsilon?
Oh, yes, excellent. Nisha had the closest answer.
Nice.
However, this the standard error is actually it'll be represented as square root of error squared. So it's the geometric average of the error. So it's not the regular mean or average of the error, but the square root of its square. So based on the standard error, we can also calculate the R square and multiple R out of it. And I'll leave this practice to you if you want to find out the relationship between these two. Basically, with the same Y or dependent variable, if the standard error is smaller, then the model would be better. If it's larger, then the model will leave a larger proportion of variation in Y not explained. So the standard error represents the unexplained part of the variation. All right. Second part of the summary output is ANOVA. All of you have done really well in representing the first part, the regression statistics. I think we haven't really studied the ANOVA part, but does anyone know anything about the ANOVA section and want to interpret some of the statistics here? Hello, John. Any?
I'm going to say no. Sorry.
Did we study anything about the ANOVA table here?
He touched on the SS and MS. I just don't recall details.
Yeah, we haven't gone through this yet. He said we will.
Yeah,
Oh,
the
okay.
video. Yeah.
All right, excellent. Then we can leave it for later. But we can also have a preview here. The DF here is degree of freedom. Based on this, we can also know the observations. So the regression here represents the number of predictors we have because we only have the weight. So that's why regression here has 1. Residues is the difference between observation and the number of estimates we have, because we have both intercept and weight as the coefficients, 2 coefficients to estimate. So if we take 2 out of 10, then that's why we had residues here. And this total will be always observations minus 1. And we will learn about these sum of squares, mean sum of squares, and F statistic, and the p-value of F, which is referred to as significance F here later. However, this area basically showed us whether this model is useful at all, whether any part of the Y variable can be somewhat explained by the predictors. As we can see, this model explained some part of it. So this model is useful than nothing. All right, last part is the coefficients. In addition to the coefficients we already interpreted, we also have a standard error, t statistic, p-value, and lower and upper lower and upper bounds. Can someone volunteer to show us what these statistic reviews or let me know whether we learned anything about these.
I don't think we've learned any of those.
Oh, we haven't. Okay. All right. Then best to leave it later. But if you wanted a preview, you can also have a short introduction. First, standard error is similar to this standard error, except that for here, the standard error is for this coefficient. And if we divide coefficient by the standard error, that's the t statistic. We can actually test here if we calculate the value by dividing the coefficient with standard error. That's how we found we can find the t statistic. If we do the same for the second coefficient, we get the same stuff. So the t statistic, also referred to as t ratio, is basically the ratio between these two. And if it's very large, we say that it's a significant coefficient. And if it's very small, then we say it's not very significant or non-significant. Then we tell the significance by p-value, and based on the standard error, we can also calculate the confidence intervals. We will discuss about their details in future lectures. And thank you for joining with me, and thank you for the questions, and I will practice, and I hope it's helpful.
Yeah, it was, Jerry. Thank you for your time. Have a good night.
You too, John.
Night.
Thanks, Jerry.
Thank you.
That was helpful, but I'm a little more confused now. I have to go back and look at the definitions again.
Well, maybe consider Wikipedia. I actually visit the web page a lot.
Okay.
Yeah, thanks, Jerry.
Thank
Yeah,
you.
Karen, if you want to chat, let me know. I'll be up. Doing the same thing.
Okay, thanks.
All right.
Good
Thank you,
night.
Donna. Bye-bye.
Bye, guys.